In this video, we will discuss hyperparameter optimization using PSO. So here we will use a numerical example to explain how we can optimize the hyperparameters using particle swarm optimization. As you can see in the previous video, we discussed hyperparameter optimization and we created a hybrid approach by combining deep learning with particle swarm optimization. And we discussed certain steps to perform hyperparameter optimization using this hybrid approach. Now we will use a numerical example to explain step by step how we can perform hyperparameter optimization using PSO algorithm. As you can see in part 1, we use two different examples. First example where we have a small data set and we have two features: size of the house, that is in square feet; second feature, that is the number of bedrooms; one target variable, that is the house price. So we want to predict the house price. Second example we use here for the image classification, where we have given a data set and we have to identify different flower from the images. So in this video we will continue the first example. We will apply PSO to optimize the hyperparameters of CNN for predicting house prices. We will map the hyperparameters to the particle dimension in PSO algorithm. Now let's try to understand this step by step how we can do this. So first you can see the basic structure. We have here input layer, hidden layer and the output layer. In detail we already explained everything about ANN, its layer in the part 1. So here you can see we have three layers: input layer, hidden layer and the output layer. So we have in the input layer, we have two features: size, that is the size of the house in square feet. Second feature we have here room, that is the number of bedrooms in the house. Then we have the hidden layer. After that, in the output layer, we have one target variable that will give the output, that is the price of the house. So next you can see the hyperparameters that we will optimize. So for example, we will use here just four hyperparameters that we will optimize. First we have the learning rate. Second we have batch size. Third we have the number of layers. The fourth one we have the dropout rate. So first parameter we have the learning rate, that is used to control the step size during gradient descent. Second parameter we have here batch size, that is the number of training example used in one iteration. Third parameter we have here number of layers, that is the number of convolution layer in the network. After that we have the dropout rate, that is the fraction of the input units to drop during training to prevent the overfitting. Now in this table you can see the range that we will use for each parameter. For the learning rate, it is between 0.0001 to 0.01. For wedge size, 16 to 64. For the convolutional layer, 1 to 5. Dropout rate, 0.1 to 0.5. So now we have the problem. You can see, suppose a data set we have with two features: size of the house, that is in the square feet, you can see in the table. Second feature we have the number of bedrooms, and we have third one target variable that we will predict price of the house, that is house price. Here you can see in this table we are using the hypothetical house price data set with features, size and bedroom, and we have one target variable, that is the house price. After that we have basic CNN structure. In the input we have size and the bedrooms, that is converted to an image like format. Next we have the convolutional layer. Convolutional layer, that is the number of layers to be optimized. Then we have the dense layer, that is the output layer to predict the price. Now we will try to understand this process using PSO to optimize the hyperparameters of a CNN for predicting the house prices with a simple example step by step. First we have the problem that we know. So we have here small data set with two features: size of the house in the square feet, number of the bedrooms, one target variable, that is the house price. So here you can see this table, we have the data set. Now step by step we will discuss this numerical example. So first step we have the population initialization phase, where we will initialize the population for the particles. So here each particle in the swarm represent a set of hyperparameters. And for simplicity, we will use the number of particles here, 3, and we will initialize the initial velocity for each particle, 0. And here we have the number of dimension, that is the number of hyperparameters. So we have 4. So number of dimension we have 4 because we have 4 hyperparameters to optimize. So number of dimension is equal to 4. That is the learning rate, batch size, number of layers, and the dropout rate. So we have population size 3, number of dimension 4, initial velocity for each particle is considered here 0. For the first particle, you can see the position. We have 4 dimension, so here it is 0.01 first hyperparameter that represent the learning rate, 32 that is the batch size, 3 that is the number of layer, 0.5 that is the dropout rate. So suppose this is the initial position for the first particle and we have the initial velocity for this particle is 0. Like that we have the position for the second particle and for the third particle. First parameter learning rate, second batch size, third number of layer, and the fourth one that is the dropout rate for each particle. After that we will evaluate the performance. It means we will calculate the fitness value for each particle. We initialize their position. Now we will calculate their fitness. Now we will check how fit each particle is. So for that we need a objective function, or you can say the fitness function, to determine the fitness of each particle. So here we are using the mean squared error on validation data. So as we are training the CNN model, so we need accurate result. So here we will check the accuracy. So here we will calculate the mean squared error. So for each particle, we will use the hyperparameters to train a CNN and evaluate its performance using a fitness function that is used here, mean squared error on the validation data. Done. Suppose we are doing the evaluation for the first particle. So we will train the CNN with specified hyperparameters on the training dataset. After that, we will evaluate. It means we will compute the MSE, that is the mean squared error. So here for the first particle, you can see hyperparameters we have 0.01, 32, 3 and 0.5. So we will use these hyperparameters and train the CNN with specified hyperparameters on the training dataset. After that, we will evaluate the CNN performance on the validation dataset to calculate the mean squared error. So here you can see the formula that we are using here to calculate the mean squared error. N, that is the data point, this is the actual value, and this is the predicted value. So now we will predict the prices for each particle. So first we will assume the predicted prices for each particle, because you can see here in this formula, when we are computing the mean squared error, it is actual price minus predicted value. So initially we will assume the predicted prices for each particles, that you can see here we have the actual prices and the predicted prices for first particle, second particle and the third particle. You can see we will compute according to this formula. So first we will compute the error, that is actual price minus predicted price. So here we will compute this for each dimension. So here we have n, that is 4. So 1 to 4 we will calculate the error 1, 2, 3 and 4. After that we will square the error. Here you can see in this formula we will square the error 1, 2 and 2, 3 and 4. After that we will calculate the sum of the squared error, that is the sum of squared error 1 plus squared error 2 plus squared error 3 plus squared error 4. So put all the values here. After that, we will compute the mean. So finally, mean squared error, sum of the squared error divided by 4. Value for n, we have 4. So we will divide the value by 4. Mean squared error for the first particle, that is this one. So like that, same we will do for each particle. We will calculate mean squared error for the second particle, for the third particle. It also depends the type of data set you are using. Accordingly, we will use the values. So here we will consider just the simple data set to show how this is working. So you can download the actual data set and then apply this data set to solve the problem, or any data set that you're using on your project. So like that, we will calculate the mean squared error for particle 2 and particle 3. So here we computed. After that, we will update the velocity and the position for each particle. And you can see according to PSO, we have certain steps to follow. That is the main loop started here. So for each particle, we will generate a new velocity. After that, using this formula, we will calculate the new velocity for each particle. Then we will calculate the new position. In the previous position, we will add the new calculated velocity and then we will update its position. Now we got the new position, so we will evaluate it again using the objective function. We will check the solution fitness. We will check whether the new solution is within the boundary or not. After that, we will update the local and the global best. Repeat until the current iteration is either less than or equal to maximum iteration. And when the stopping condition is satisfied, we will stop and display the best solution. That is here, the best hyperparameters. You can see in the velocity formula, we have W, that is the weight inertia, and value we're using here 0.5. Then we have two coefficients C1 and C2. C1 0.8, C2 0.9. Random value we have R1, R2, that is normally distributed between 0 and 1. Suppose R1 is 0.6, R2 is 0.4. Now suppose the next position that we obtain for the particle is here. This one, the velocity is this one, and here we calculated the mean square error for first particle, second particle, and third particle. Like that, we repeated this for the second iteration, for the third iteration, and after that we evaluated the performance, and according to PSO step, now we will update the final global best. So here you can see among all the particle P1 having the best parameters, you can see the it having the mean square error, that is the minimum among these two particles. So here we will consider this first particle as the best solution using the hypothetical predicted prices to calculate the mean square error for each particle. You can use your own data set here. So here you can see these hypothetical predictions. So in real world scenario, you can train the CNN on the data set. So you can see this PSO algorithm iteratively updating the hyperparameters and minimizing the mean squared error. So in this example, we try to understand how different hyperparameters for CNN affect the predicted accuracy of the house prices and as evaluated by the mean squared error. And we used here PSO where we represent each particle as a different set of hyperparameters, and we calculated for each particle the mean squared error. After a certain iteration based on the mean squared error value, particle P1 it produced the lowest error that indicate that its hyperparameters were the most effective for predicting house prices in this example. This is the simple example that how we can use PSO to optimize the hyperparameters in CNN, and we can improve the model performance. So by iteratively we can update the particle position for 1000 iteration. So based on their individual and the collective performance, PSO will converge toward the optimal set of hyperparameters, is improving the predicted accuracy of the CNN. So that's all about this video. If you have any questions, you can comment below, and thanks for watching this video.